Hi, my name is Rishi Sinha, and I'm going to be discussing automated contact tracing in the face of COVID-19 for the AT&T Oxygen Scholarship. So what is contact tracing? Pretty much it just flags everyone coming in contact with an infected person so that they don't spread infection. As you can see here, we've mapped out like all the infected people, and the way contact tracing works is it just sees everyone that they've come in contact with, and we just try to catch those people before they spread it to more individuals. So why do we need automated contact tracing? Uh, there's two issues. First of all, there's just too many people for human contact tracing. Just remember, just like people that they've sat next to on the subway, or just like other random individuals. And in addition, the human memory is just people don't all often recall everyone that they come in contact with within a 2 week span. So what was I working on? I was working on a Bluetooth-based automated contact tracing approach called MIT PACT. PACT stands for Private Automated Contact Tracing. And then the thought process for this is that, so pretty much how it works is just two people will have devices that are always emitting and receiving Bluetooth signals. And the intuition that is that a weak Bluetooth signal means that they're far apart and there's no contact. And a strong Bluetooth signal means that they're nearby and there is contact. Uh, Unfortunately, there are some challenges. The signal is affected by obstacles. As you can see here, the two devices are in backpacks, which means that there might be a reduced Bluetooth signal, even though there is contact. And here, even though there's a barrier, uh, there might be a strong Bluetooth signal, despite the fact that there's no contact established between them. And regarding COVID, at least, so like the disease won't spread through here. However, this doesn't mean that this is a completely useless task. Automated contact tracing is meant to complement human contact tracing, so it doesn't have to be 100% accurate. If we can automate even just 70 to 80% of the hard cases, of the easy cases, then human contact tracing can handle the hard cases. We just want to make this process more streamlined for making sure that we catch more of everything and we have a wider net. So pretty much my research was into collecting data on the effect of obstacles and distances. So I had three different distances, 4 feet and 6 feet, which I classified as within distance and established contact, and 8 feet, which was without distance. And then I used different obstacles, such as none, a backpack, a knapsack, a drywall, glass door, or a solid wooden door. As you can see here, it's just a glass door. And the devices that I was using were Raspberry Pis, and I was just measuring the signal strength between them at these different distances and with these different obstacles. And then I just plotted this out using matplotlib. So the brown bars were no contact, and then the blue bars were contact. Obviously, we'd love it if there was no overlap, but as you can see, there is a lot of overlap that we had to deal with. And then the final part of my project was applying a machine learning classification. So I trained on 60% of the data and then tested on 40% of the data. And then I used just different machine learning classifiers using scikit-learn. Standard machine, and you can see here some of the decision trees on the right. Standard machine learning algorithms can correctly predict about 70% of the time. That's what I found out using my research. So it can complement human contact tracing and reduce their workload. And there's a trade-off between a lot of wide availability and accuracy. So there are other signals that might actually be more accurate, such as ultrasound, but Bluetooth is more readily available with cell phones. So that's why we decided to use it. Thank you for listening, and I hope you consider me.